Okay. Let me just try and describe to you the formal construction for the integers, and kind of like maybe like a to-do list of, the typical things you'd want to prove, you know? So first we might construct a set S. So let's define S to be the set of all ordered pairs of natural numbers. Okay. And we need to define an equivalence relation on S. So let's call it tilde. And how do we define it? Well, just like things in S are going to be like differences of natural numbers. So two differences should be the same if they should have the same difference, you know. So we want to say like M, the difference of M and N is the same as the difference of K and L, if and only if right. So M plus L should be equal to K plus N. In other words, M minus N should be K minus L, except that we don't have a subtraction, you know? So we're doing all of this so that we can write things like M minus N, you know, but in our brains, what we're trying to achieve is stuff like this. Okay, so with this goal in mind, well, we bring the L's and the N's over to the other side. And now this is an equation that's in the natural numbers using addition. So this is all perfectly valid. Okay. And then we define, so we have like a proposition. Twiddle is an equivalence relation on S. And the proof the tough one, I mean, the proof uses all these different properties of addition of natural numbers. So let's just like sketch the proof. Like reflexive is easy. Symmetric is not too hard, but the tough one, I guess, would be transitivity. So, you know, let's suppose M, the difference of M and N is the same as the difference of K and L, and also that K and L is like, I don't know, UV. Okay, and we have to show like Mn is the same as U and V. So we have M plus L equals K plus N, and we have K plus V equals U plus L. Then we add both of them. Wait, what should we do? What we should do we should add both equations. So we get M plus L plus K plus V equals K plus N plus U plus L. Okay, and now to go further, So we would need things, if we did this, we'd need things like the associative law, commutativity, and things like this. These are all things that you can prove for addition of the natural numbers. Then assuming those, what happens now is that you have the cancellation law of natural numbers. Once you can cancel k's on both sides. You can cancel l's on both sides. And then you have m plus v equals n plus u. Or in other words, m plus v equals u plus n. In other words, that the difference of m and n is the same as the difference of u and v as required, proving that this equivalence, this relation is a transitive relation. Okay, so this proof requires commutativity. That's too many t's there. But anyways, it requires like m plus n equals n plus m. It requires m plus n plus k. It also requires the fact that m plus k equals n plus k implies m equals n. These are all things that you can prove, like, in the usual way by induction. And once you do that, then you can construct, once you prove all the required properties, you can prove this property of the integers. Okay. So once you have an equivalence relation, that now you have something to work with. So now you define the integers to just be the ordered pairs of natural numbers and then you take the equivalence classes according to this equivalence relation. Okay. So now an integer is just a difference of any two natural numbers. And now you have a set, right? Okay, so these things are supposed to be supposed to be integers. And then so you need a way to think of a natural number as an integer. So you define phi from the natural numbers to z. And you take a natural number and map it to the difference of n and 0. Or the equivalence class of n and 0. Okay. And in that way, you identify a natural number with an integer. And then you would show proposition phi is 1 to 1. And then you'd also show that, like, anyways, you'd start with that. Okay. And then what that tells you is that now you can really think of the natural numbers as being a subset of the integers. Okay. But not, so I'll put this in quotation marks, because this is not really a subset. We think of, we identify certain integers as natural numbers. Any integer that can be written as the difference of n and 0, we call that a natural number. Okay, so we think of the natural numbers as living inside the integers, even though it's not literally true that they do. We identify certain integers as being natural numbers, and then we would want to like make sure that anything that holds for the natural numbers over here also holds for here. And we need to define like addition of integers. So we define, the addition of nm and kl to just be n plus k, m plus l. Okay, this is, and then you'd have to check that that addition is well defined, basically. So you have to check that if nm is the same difference as n prime m prime, and same for k and l, then when you sum them, you get the same thing. Okay. And that would give you addition. And you do the same thing for, try and do the same thing for multiplication. It's a little bit more complicated. For multiplication, you just expand that, and then that should tell you like how to define multiplication, because once you expand it, you get nk plus ml minus mk minus nl. In other words, the product of two differences is the difference of this minus this, right? So you should define nm times kl just to be nk plus ml mk minus nl. Oops, sorry, mk plus nl, right? And so in that way, you define multiplication of integers. Then you have to check that that's well defined. You assume these two properties, and then you have to check that when you multiply this times this, you get the same integer as this times this. Okay. And there's many other things you have to do, like just to give you another example, you then show that you can write the integers as the union of the positive integers, the integer 0, and the negative integers. And once you define what the positive integers are, and you prove that any integer is either positive, 0, or negative, then you can define an order on the integers, like less than. Then you can prove that the integers are linearly ordered. Okay. So, and then, you keep on going this takes a lot of time. Okay, so I guess I've gone on too long. I'll stop there. On next week, or maybe just in a quick video, I'll kind of try and tie up any loose ends with the integers and the rational numbers. And then next week, we're going to move on to the real numbers. And we're going to do that in more detail. I just wanted to give you a rough idea about how to use the natural numbers to construct the integers, for example. Okay, so that's it for today. Yep. Thank you.